Okay guys, Dave Shopius back again. Sorry about that. My other memory card filled up and it stopped. I think we are at the wrist motor. I just want to recap that. Again, the claw motor, I'm sorry, the claw servo. That's just a mini servo in there. I've got built up with the Octobot spacers and polycarbonate piece of Lexan that I cut out that slides up into between Bill K's claw. That's how that works. I'm just doing it by hand right now. You see how kind of I took all of Bill K's metal bolts out and put nylon bolts in there, so it's lighten it up and makes it slide a little bit better. Those are nylon self-lubricating and everything, so it works out pretty nice. I think I covered everything. Here's that door bolt that I put in there that slides back and forth. You can kind of picture how that works. And this thing is like 4 inches long, so there's plenty of support there, this thing, and it's all solid brass. It's light and strong. I had to do some work on it up here just to get it to pass. Again, this thing's just been holding by itself all this time. There's no power on the motor. I do have this servo going right here just so it doesn't flop back and forth because I got no springs on it. So that servo there is powered up and holding. You can feel it. It's just a standard servo. These are high-tech servos I'm using. They're all the strongest in their class. Lots of torque, lots of power. Getting back down to the motor. Let me bring it back down. This is my Easy Builder software that's running this thing. I'm going to center this. Bring it down, see how nice and smooth that is. I had the scripts I have are just crude right now. Very crude, so they need a lot of work. They're just basic movement scripts. This is something else that my machinist turned me on to. The other hubs that I was using on this were just tearing up the motor shafts. So he says, hey, why not get a taper bearing? And that's what this is. It's just a taper bearing that's sized for the shaft, which is I think 11 millimeters on this AMA 226 long nose shaft. I'm going to end up cutting this off. I just haven't done it yet. This will be cut off even with that taper shaft. What that does is it's two-piece. It's this outer ring right here, and this inner piece that goes onto the shaft over the shaft. My machinist milled it so that you can see it's just a sprocket that I got, and he milled out this hole right here on this aluminum plate, cut it all up really nice, and it's just a matter of slipping everything together. He drilled and mounted around here, and the taper shaft goes in, is held in by these two set screws here, and the thing just squishes down and hugs that bearing, hugs that motor shaft, and just grabs onto it like a lock. You can't budge it. You can't move it. I mean, I can lay on this thing, it won't go, and you can have this thing rocking back and forth, and it is not going to budge. It doesn't damage the hub. To get it off, I just take these two out and run one in here, and that thing just pushes out and it comes apart like glass. So it's all milled together. The other thing that makes this thing works really good, well, before I talk about any of the control, I just want to give you a demonstration of how this thing works, okay? Because I know you guys are interested in that. Again, it is powered through Easy Robot. That's the Easy Bee sitting right there. I am powering it with a 30 amp power supply, a switching power supply. That's powered right out of the wall. The battery is, because this Sabertooth has regenerative functions that if it puts power back in to keep a battery charged. Well, I'm not using a battery, I'm using a power supply, but I have to have a place for the power to dump into, or else it's going to kick that out and I won't have any power. But anyway, it's powered through that battery to here, to this Sabertooth with regenerative powers that goes back, dumps extra power back into here. That's a little Kangaroo daughter board that gives the Sabertooth position and speed control, which means I can put my arm at any position I want according to the software, and it needs feedback though. And right now I've got it hooked up to a couple of limit switches here that tell the board where the end of the stroke is, and I also have a little flat potentiometer in there that gives the board feedback. I'll show you that in a minute if I can remember. But that was another little trick, finding something to get feedback and plus be able to fit it into that arm right there. So anyway, EZB software. Again, I can go take the arm up, take the arm down all the way, see how far it goes down, and I actually have that cut out in there so it will go down, so I can get full extension up and down. And I'm going to bring it back up to the center. And that's the elbow joint. The wrists, hopefully I can get this and shoot at the same time. You know, I'm having issues with the wrist. Hang on a second. Again, I got bugs to work out. There it goes. You can see how the wrist works. It has pretty much a full range back and forth of a human wrist. Trying to do this with one hand, this is insane. So, but you guys get the idea. You know, it's really pretty reactive. And then as far as up down, I'm going to take it up a little bit because of that thing I'm underneath. I'm just doing this all through EZB software manually. These are no scripts. And then let's see if I can show you. Here, let me take it up. Sorry guys. So you can kind of see how the you see how that pulls out of the way? Okay, I'm going to reset everything to the way it's supposed to be, or close to it. And I'm going to show you a little bit of a routine that I got written. It's just a basic movement routine. Claws open and close. I'm going to start these one at a time, just kind of give you an idea. You saw this before in the other video. Yeah, that buzzing you hear, that's that digital servo. That's the only digital servo I have in there. And that's holding position, that's normal. Okay, I'm going to start up the routine for the wrist now that I have. show you from underneath here, hopefully. See, that goes back in. She settles down for support. Out of the way. It comes down. The other side. Hello. Hello. Pretty cool stuff. No, we don't have the elbow working yet. But this little thing here kind of gives it that snake look that you were seeing in the first video. So you'll be able to reach around, touch both claws. Both arms will run independently. Here's that. You see how fast that sucker's moving. For 7 to 1, that's just insane. And that's full speed. The other thing I did is I mounted that wrist servo sideways to give it more support, shorter arm clearance. I saved a couple inches that way too. I mean, I had it first pointed straight out from the arm, and that really extended it out. This brings it in closer and tighter. It gives it more support, and I was able to support it fully without any kind of pressure on that little servo itself. You see how that thing's working in there? I've got about a ½ inch of bearing up here from top to bottom on that servo horn, and that just gives it all the support that this 3-pound claw needs. So that's how that works. Now let's get the you can see the little guy in there working. See, back and forth. Get it out of the way so she can come down. Again, this is just a crude routine. I'm going to get the arm going too now. The elbow, rather. Whoops, there you go, way down there. Now this will allow him to reach up and reach down. Scratch his bubble, scratch his butt, whatever. While that thing's rocking up and down, let me show you a little bit about the control. Again, I alluded to it before. You got your, I'm not going to go over this again, but you got your saber tooth that's controlling the DC motor, and that's it. EasyBee, the Easy Robot Builder, it is operating and controlling the servos. It is also sending, Easy Robot is also sending serial commands to the Kangaroo to tell it where it wants the position to be on the elbow motor. And the Kangaroo knows where the motor is all the time because of a little potentiometer that I have in there. It's just a little flat potentiometer. It's called a soft pot. They cost about $6 a piece. It fits right in there. That's all it does. See how thin that is? And this is a sticker on the back. It just sticks right to it. And there's a little stylus that you can see right there. That I have my machinist screw a hole in through everything. And that little stylus, it just, you can't see it because it's so tight in there. It actually runs around this potentiometer and touches it, and just that simple contact tells the Kangaroo through these little leads right here where that arm is at any time. It's pretty freaking cool. Just amazing that that little bitty thin thing can do all that. You have to be careful though. One thing you got to do is put a resistor, a 10K resistor, on one of these leads here. And I put it right here on one of these power leads. It'd either be the power lead or either side, the power or the negative. It can't be on the signal, which is the center. Because the problem is, if you touch both of these together beyond here, you'll end up burning it out. See that little guy right there? I burnt the hole right in that sucker. And that was because I pushed the leads together right here. There's a resistor up in here, but there's no resistor down here, so if you put the two leads together, that little sucker will get hot and burn right up, and you'll get a hole right in that sucker. See there? It's just, whoops. Anyway, $6, gone. This one here had a defect in it. I think I had a bad lot, but that's the third one I got in there. You can see the tail of it sticking out right there. So anyway, that's my arm. This it's not getting hot at all. Blue. If you want to see more about the controls, I know that's a mess. It's all stuck together with wires and stuff. I'm going to be cleaning all that up. There's the skin that'll go over it. I did a video before. I'm going to bring this all to a stop now. And you can see, there it is. Crude. But effective. So anyway, there it is. I don't like that whining. Got to figure out a way to take care of that. Right now I just do that by unplugging. And you see what happens with that thing's not locked out. If I don't have that little support in there, she just sags down. So that's what that little support is for, that you saw in and out. The thing the weight of it just draws that guy down. I'm going to release all my servos so I'm not using any energy here. That's it. They all went red. Now, if you want to stick around a little bit, I'll show you some of my earlier prototypes. Remember, there's the final version. I'll probably be changing it again, knowing me. But I started out last year building this little guy here. It's just a DeWalt 24-volt motor. By the way, the ones I'm using now are 12 volts. The AME are 12 volts. That's a DeWalt 24-volt motor with a little hand-built bracket. It worked okay, but I didn't know how strong I needed it back then. And this DeWalt just wasn't doing the job. I was having problems with feedback errors and tuning the Kangaroo. So I got the AME. This is the 218 series. Powerful little motor, but the problem with this 218 is it's not quite powerful enough. It just didn't have the guts, I'm sorry. Edit that out. It wouldn't hold the load when it was done. If you see here, this 226. That one there is just holding the load perfectly. The 218 would sag down like this was. That was not good for me. So I needed a stronger motor that would hold the load. So I went to my next generation. I figured, okay. Oh, and the other thing is this bracket here just was flexing too much, and it just wasn't holding everything straight and in line where that little soft plot could get an accurate reading. So I was getting errors. So I thought, I'm going to get myself a piece of angle iron. So I got a piece of 4x4 angle iron. Cut out a piece of 4x4 angle iron on my bandsaw. Hit it with a file. And this was my first really good prototype that I took to the machinist. You can see the problem is here, I had two issues here. This joint here, this bushing, was not going to hold up over time. The other thing is that you can see how this thing worked. It just like the other one, picked the load off the top. The motor shaft is too short to come through the way I needed it to. This aluminum hub couldn't put up with the load that I was putting on. You can see it's kind of oblong and wallered there. It just wasn't a good deal. The hole that I had for the stylus, for the soft pot, I couldn't get that exactly right. I was just having all sorts of problems, so I took this to the machinist and I says, hey, I need something better. He turned me on to this. This is the final version. Here's that taper bearing that I was talking about, how he's got it milled right into there. Don't even need a lock, don't even need a shaft, don't even need a key. This thing locks down so nice, but it's got a spot for it. You can see how nice that just slides on. The soft pot goes in here. Mount my limit switches. There's the bearing. And the 216 long nose motor. I'm sorry, the 226 long nose motor. When it's cut off, will be just fine. So that's my little museum. I had one more prototype before this. It was just a couple of motors, small motors bolted together. I got a video of that too. That was an epic fail. So the other problem I was having with this motor right here was it was chewing up this hub right here with that set screw. Not good. It chewed up the motor shaft. You see it's got these D motor shafts. You really need a key for this kind of load and torque, or a taper shaft, which is the most elegant way to do it. It's just amazing. My machinist is just fantastic coming up with that. So I'm running out of battery. I've got to go now and watch the Packers beat the Dallas Cowboys. So I'll see you guys later and let me know what you think of all this. Okay? Bye-bye.